In this video, we're going to be talking about dependency grammars and dependency parsing. This is an alternative to constituency grammars, which have internal nodes in which the tree has non-terminals that describe how words fit together. We're not going to see any of that today. Instead, we're going to take a more minimalistic approach to linguistic syntax. One of the basic ideas of syntax is that words don't stand on their own. They're connected by some hidden structure that connects the words to each other. The goal of dependency parsing is a fairly minimal representation of the connections between words. Build a tree out of the pairwise connections between words. These connections are defined in terms of connecting heads to dependents, where both the heads and the dependents are words in the original sentence. So how do we define heads and dependents? A dependent usually tells you something about the head, how an action was done, where an object is, or what kind of object you have. Here's an example of a sentence labeled with dependency arcs. The labels correspond to the exact relationship between the head and the dependent. For example, India is the subject of the verb won. That verb is also connected to the object. And you see that it's not just any cup, it's the World Cup. But this is cricket, not football, just in case you were confused. But what's that thing off to the left here? Trees need to have a single root. So we're going to assume that every dependency tree has an artificial root here. It usually connects to the main verb of the sentence. You can see how this might get complicated if we had multiple independent clauses. But what if you need to find, for example, a phrase? For that, you need to find the head of the phrase and then look at all of its children. For example, you have the prepositional phrase, by beating Sri Lanka, that is defined by all the children of by, including by itself. And you have a noun phrase, the World Cup, headed by cup. So that's the big picture, but how do you know how to point these arrows and where to put them? What's a head and what's a dependent? There's a lot of debate about this, but there are some high-level rules for when D is a dependent of head H in construction C. If the head determines the syntactic category of a construction and can replace the construction, that's a good sign that it's the head. If you have dogs with a shaggy fur are fun, you could just replace the whole construction, dogs are fun, and it's still grammatical. If H somehow gives the semantic specification of C, and the dependent specifies H, you probably have a head-dependent construction. If you have a gray dog, that specifies what kind of dog you have. The head in a construction is usually obligatory, but the dependents can often be optional. So we could get rid of gray and just say dogs. So if you have the sentence, my gray dog is named Bob, you can say my dog is named Bob. But you can't say my gray is named Bob. H selects D and determines whether D is obligatory. Selectional restrictions are an example of this. You can eat food, but you can't eat shares. This is saying that the head, the verb eat, specifies what kind of objects can be used in the construction. Transitive verbs are an example of this. Some verbs need to have an object, other verbs can never take an object. And some verbs take objects sometimes, but not others. In all cases, what verb you have, the head, determines whether you can have a direct object, an indirect object, or not as a dependent. The form of the dependent also depends on the head. So for example, in Romance languages, you have inflected adjectives that take a form that depends on what it's modifying. In other words, it reflects both the gender and the number of the head. For example, in French, a dangerous liaison is a liaison dangereuse. Apologies in advance for my horrible pronunciation. But a dangerous dog is un chien dangereux. You can see that the endings are different. We also kind of have this in English for an apple or a pear, but it's far less frequent. The position of the dependent in the sentence is also specified with reference to the head. For example, in English, our adjectives come right before the noun they modify. We just saw in French that the adjective often comes after the noun. Languages usually have a preference for where those modifiers go, but it's always in relation to their head. In many cases, it's clear what direction the relationship should go, which is the head and which is the dependent. Objects of verbs are obviously the dependent of the head verb. Adjectives are obviously the dependent of the head noun. But other cases are a lot trickier. For example, complex verb groups. If you have a construction like can see, which of those should be the head? In this case, we'll usually say that the helper verb acts as a head. Another tricky case is subordinate clauses. We'll use the convention that the word that introduces a clause acts as the head. Similarly with coordination, if you have two words joined by a conjunction, we'll say that it follows the linear order. That if you have A and B, A will be the head, the conjunction will be in between, and the second object in the coordination will be the child of the conjunction. This is all fairly arbitrary, and we'll see that reasonable people can disagree about this. Prepositions will assume that the preposition itself is the head and the object of the preposition is the dependent. Punctuation is super arbitrary. We'll say that it's related to the main verb of the sentence. Really for lack of better options. So more concretely, the problem of dependency parsing is taking an input sentence and then getting this output in a graph form that connects the words together. We'll talk about some of the constraints on the kinds of graphs that can be generated by a parsing algorithm. But to do that, we'll need to introduce some notation convention. First, we'll introduce the idea that a word is connected to another word in an unlabeled dependency. When we do that, graphically, we'll draw an edge going from the head to the dependent. We'll often distinguish left versus right edges. If I is greater than j, it's a left edge. If j is greater than I, it's a right edge. And this is simple, it's just which way does the arrow point. And we'll often provide a type k for each dependency edge. This tells you what kind of relationship connects the two words together. A dependency parse is only complete when all of the nodes are connected and there are no cycles. Let's go through these conditions a little more formally. We say that the graph is connected when, for every two words, there is some sequence of edges going between them, including ignoring direction. And then it also needs to be a tree. There needs to be a single head and no cycles. Otherwise, it wouldn't be a tree. Finally, many parsing algorithms assume that a parse tree is projective. You may be more familiar with this concept as planarity. You can draw a tree over this sentence without crossing edges. More formally, if you have an edge from I to j, then anything between I and j can't have an edge that goes outside of I to j. This is easier to see with an example. So here is a rare non-projective sentence in English. A hearing is scheduled on the issue today. The edge going from scheduled to today crosses the edge going from hearing to on. And so this makes the sentence non-projective. For English, the vast majority of sentences are projective, so it's often simpler to create algorithms that create projective parses. They're faster and have higher accuracy. So they'll only output projective trees. However, this isn't a good assumption for languages with freer word order or long-distance dependencies. Czech is probably the most famous example of this in NLP history. It has a very high percentage of dependencies that are non-projective. And when you run a dependency parse, you typically compute an accuracy at the edge level. How many of the edges did you get right? And of those, how many also had the head assigned to the right label? But other times you want to evaluate on the downstream task, like you're doing question answering, information extraction, and so you don't really care about the underlying parse, just did it help you figure out who did what to whom. By now, you're probably getting the sense correctly that dependency parsing can be quite different in different languages. I just made a bunch of declarations about how we're going to do it for English, but different languages can and do make different decisions about how to do it. And different people parsing sentences in English have disagreed with the things that I just declared we'll do for English. For example, here are 3 sentences parsed for dependency parsing in English, Swedish, and Danish. For example, the good people that parse this Danish sentence put the determiner as head of what we'd call in English a noun phrase. And this makes sense. You know the gender given the determiner. Thankfully, everybody agrees on how to deal with verbs, but conjunctions are handled in 3 different ways. Sequentially, with the conjunction as the head, and with nouns as the head, and with the conjunction modifying the first noun. But thankfully, folks are working on creating a universal set of dependency annotations that creates a mapping between languages with the following properties. The data are thankfully available online, and it's an excellent way of being able to see both the similarities and differences between language through the lens of syntax. To wrap up, in this video we talked about what a dependency parse of a sentence is, and now you should be able to identify, given a pair of words, whether there is no relationship between them, or which one is the head and which one is the dependent. Now you're prepared to learn about the algorithms we can use to create a dependency parse of a sentence. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.